Thanks for coming to my talk. I'm Pittman. I'm one of the AJUG and DevNexus organizers. I'm a senior software developer at Red Hat. I work on the AeroGear project. I'll talk about myself more in a minute. The topic of this talk is developing compilers and tools for the JVM. I'm going to be presenting a very simple compiler for a language called Tiny, as well as some simple NetBeans tooling. Those two are the two GitHub repositories. If you look at me at GitHub at Second Son on GitHub, you'll be able to find those, and these slides will be sent out to the mailing list afterwards, so you'll be able to get them later. The obligatory biography. As I said, software engineer for Red Hat. I mostly work on Android and Java things with a smattering of web technologies and other things. My hobbies are AJUG, cycling, coding, and a few other things. I actually rode my bike 20 miles-ish here this afternoon, so I had one fewer car on the road for those poor people on 400. Compilers and tooling is a very, very broad topic. There are literally not just books, but entire courses and degrees in this field. The goal of the talk is not to tell you everything there ever is to know, but to give you somewhat of a broad survey and show you a very practical example. This talk actually leaves out compiler tooling. And by that I mean there's lots of generators to help you take some of the grammars and the core features of a programming language and automatically generate the lexers, the parsers, the scanners, the error correctors, the optimizers, and of course the compiler. And I'm not covering any of those because that would be another series of talks. But basically I'm going to introduce the topic, show a quick demo of the Tiny compiler and its integration with NetBeans, and then I will begin discussing, I actually have better notes on my phone, then I'll begin discussing the language and the syntax of Tiny, and how compilers work and how the integration actually hooks up with things, as well as a brief discussion on the JVM and how it works under the hood. And finally, I'll actually dive into the code. As I said, this is a very broad topic. Feel free to stop me at any time if there's something that you want me to expand on or talk about more or repeat or dive into. Quick show of hands. How many people here code for their day job? Okay, awesome. How many people here don't know what a compiler is? Awesome. Okay, that saves me a lot of time. All right, so first a quick demo. This is good old NetBeans. This is good old. Let go. Oh, I'm running the. So NetBeans language supports in these things called modules, and it has pretty good support inside of the IDE for actually sandboxing it from itself. So I'm firing up a demo IDE with my integration running. Okay. Here we are. So this is an example of the Tiny programming language. As you can see, I have syntax highlighting and all of that in there. The Tiny language is not clearly not Java. It is statically typed in that there's only one assignable type, integers. It does support Boolean types for flow control, and it has a read method and a write method hard-coded into it, which reads a line from the console, parses it as an integer, and then, or writes an integer to the console. And it's, does in fact work. I can set breakpoints, and then I can actually run the code. and the demo gods are with us today. So as you can see, I typed 4 into my console, which was running the factorial program. It caught the breakpoint. I have here my variables that are expressed in the program. I can step through it. And then see that it is going to write the variable out, continue it, and then if I go back to xterm, the output's there. Thrilling code. But surprisingly, the integration only took me a couple of days to write, and that includes learning how NetBeans works under the hood. But yeah, that is the code that we're going to be looking at. As I mentioned, all of this runs on the JVM, and all of this targets the JVM. And for doing things like, for writing programming languages, the JVM is actually a really awesome target. You get a lot of things just for free. If you include, you get debugging for free through JPDA, which is the Java something debug whatever. I'm terrible with acronyms. The Java bytecode is very similar to Java code. It's organized into classes and methods. It is very sane. It's stack-based, which is very easy to understand. What stack-based means is that you push values onto the stack, and then you push an instruction that consumes several values at once and pushes its result to the stack. This has implications later. And you get lots of free stuff. You get portability to every platform the JVM is on. If you target the JVM as the target of your compiler, you get automatic JITting, which means that your awful compiled code will be examined by Hotspot and optimized on the fly, and eventually translated to native machine code. Also, the JVM sucks. So, as I mentioned, the bytecode's very much like Java. Your types are very tied to your bytecode. So when you are writing code in a more traditional environment like C, you can do some really interesting things with casting, where basically you're just dealing with binary streams of data, and you can tell the processor, hey, read this data from this point of memory to this point of memory, and your code will treat it as whatever the code wants to treat it as. In Java, what you have to do is you have to say, take the value that's on the stack, cast it to what I want, and then perform the operation. And if you do not do that casting, you'll end up with different errors, and if it's an incompatible type. So you can't just sidestep all of this. Even with invoke dynamic, which allows us to attach methods to objects more dynamically, it's still very limited, and this is good and bad. And again, also the JVM, while it has very impressive JITting capabilities, it's still slower than native code. So yeah, moving on to the actual and I mentioned the Java bytecode before. It includes lots of things. It includes all of your methods. It's where you will also add line numbers to it using special label nodes to tell the debugger things, and the variables and other debugging information. Okay, so now we're ready to actually talk about compiling and the theory behind that. Is there anything anyone wants to ask before I continue? Because this is where the actual part of the talk is. Yes? No? Good. Awesome. Compiling is broken down into several steps. There's lexing, which is also called scanning or tokenization, where you take the individual tokens of your where you take the string version of your program and you break it up into individual chunks. The next part is parsing, where you take those individual chunks and you arrange them into a logical hierarchy, usually a tree structure, for the compiler to step through and turn into machine code. Then there is semantic analysis. This is where a lot of your type checking happens. This is where a lot of your logical checking happens, making sure that you're not trying to use a Boolean where an integer is appropriate, trying to make sure that you're not using a string where a number is appropriate. If you're doing any sort of type dynamic type changing or dynamic type checking, this is where that will start coming in. In the case of tiny, all we really do is make sure that you're using an integer where you're supposed to or not. Then after that, you have error checking and correction. That's another very complicated topic, which we're mostly going to skip. But that's where, like in JavaScript with your optional semicolons, that's where, recovering from the fact there is a semicolon missing and you know there's supposed to be one there, that's where that could happen. And then there's optimization, where you take things that could be put together and reorganized in a way where you take code and reorganize it so it's more optimized for whatever architecture you're targeting. You combine common operations, you can drop operations that are never read again, and things like that. Again, another topic we're not really going to talk about, but I can recommend some books on the topic after the talk. And then finally we hit translation, which is where we take our code tree and turn it into bytecode, where you look at each individual node. So with that kind of overview, let's get back into the nitty-gritty and actually talking about compiling and lexing. So one of the first things you have to do is know what your language is. And the way languages are defined is using something called a grammar, which is and the format of grammars is usually in EBNF, which stands for something not normal form. Bacchus, okay, Bacchus now. As I said, this is practical instead of theoretical, so like feel free to just chime in with stuff like that, because I don't remember. And for those of you who care, this is going to be a recursive descent parser instead of a table-driven parser. But I'll talk about that in a minute. So this is the grammar of the tiny language. If any of you have ever seen a grammar for a programming language before, you know that this is very, very simple. I originally wanted to use a C-typed language called C-, that's presented in the same book that the tiny language is, but the grammar for that is about 3 times as long for not much more functionality. So the items in bold are our tokens. So the way tokenization works is you begin consuming the strings, 1 character at a time, until you either detect an error or you formed a token. And then you take that token and you kick it back as a node object with various metadata attached. And that is done in my scanner class. It's actually really simple. You pass it in a character buffer, which represents the text of the program. There is a recursive function, getNextTokenString, which scans your string for the next token, breaking on white space if appropriate, or whenever it finds a full token. So in the case of if, with it an I, then an F, it knows it's if. Check, okay, there's a white space, so it's not if blah, blah, in an identifier, or there's some other terminating breaking character. And basically, at the end of your tokenization step, you will end up with a list of tokens that are either a keyword token or an identifier or a number. Number tokens have a value, which is the value of the number, and the keyword token and the identifier tokens have the name of the variable, which is a name. And then we come to parsing, which is where we take this line of tokens and arrange them into a tree structure. So if we go back to the grammar, one of the things that we can see is that we have this recursive structure here. And this defines how we're supposed to parse our code. Everything begins with a program, which is actually a single statement sequence. And a statement sequence is a, well, list of statements that, well, it's a statement, and a statement is an if, a repeat, an assignment, a read, or a write. And then it kind of becomes recursive and goes in through here. And you end up with this tree structure that looks like, see if I can just find, you end up with a tree structure that I don't have a good representation of.
Is the code we're looking at there, is that generated or is that hand-coded?
Oh, it's hand-coded. And this is the wrong parser.
So what's the point of the grammar if you hand-code that code?
The point of the grammar is to tell you what to code. So the easiest way to...
Okay, so you didn't, I should have said that differently. So
yeah.
you can communicate to people what your code is.
Right, okay, so...
You didn't generate the code.
Right. Actually, thanks for asking that, because that really helps me frame my next, the next part. So what's the point of the grammar if it's not being used by the tool, if it's being used by you? How do you read the grammar? What do you do? The easiest thing for me was to actually do this in a test-driven design style, where I look at the root nodes of the grammar, which are number and identifier, and then work my way up through it. So if we go to my list of tests, the first thing I want to do is I want to parse a constant. Constants are numbers, so 3. So what I do is I take the string 3 and then I tokenize it, which gives me a list of tokens, which includes a numeric token, the number 3. And then I run that through a parser, which consumes a list of tokens, and it returns a single node for the numerical number 3. And I can test file, debug test file. Okay. So what the node shows me is that it has a lot of information embedded in it. What kind of node is it? It's an expression node. What kind of expression in it? It's a constant expression. What's the type of the node? It's, well, node type is different. What's the operation attribute? Node type is actually defined in, is set during the semantic analysis phase. Where's the line? It's at number 1. What's the name of it? There is no name because it's a constant value. What's the value of it? 3. Does it have any children? As I mentioned, whenever you're parsing things, you're trying to create a tree structure from a linear structure. So, okay, we've got our number. Now we need an identifier. Identifiers in the tiny language are... Actually, I don't have a test for that. Identifiers in the tiny language are very similar to numbers in that the tokenizer will find your identifier, which is a variable name, and it will assign it the various types and the location it needs. So if we want, I can add another test. I can add another test and we can see what the identifier looks like, assuming I remember to remove my old breakpoint. So an identifier node is still an expression node, but it's an identifier instead of a constant. And these nodes are what we use later on when we're looking at these nodes are used by the compiler later on to determine which instructions to write. But then the next thing in our grammar is, okay, we have a factor, which is an and then the last thing in a factor is it's an expression bounded by parentheses. the only expressions we support right now are constants and identifier expressions. So we can just write another test where we tokenize parenthesis, number, parenthesis, and then run through all of that, and hopefully we will get a single token, which is a expression, and we do. And then the next thing going up is we have the multiplication operators, which are plus and minus, and then if we run through here, we can see, okay, the expression, simple expression term, a term is a factor, which is either a multiple operation, and then a factor with an optional multiple operation, then a factor. So the next thing we can do is we can do 3 times 4, 4 times 3, 4 divided by 3, and this will actually get us a tree type structure. This is the first time that we're getting a tree where we have a operation and then its 2 component, and then its 2 operands. So if we run this again, so what we expect to see is a single node, which is an operation, and it's a token, and it's a multiplication operation. And if we look at, and if we inspect the variable, sure enough, we get that. A token multiplication, on line 1, the number 3, and then on line 1 again, the number 4. And okay, so we've got multiplication, we've got factors, great. Now we have to deal with addition and subtraction. And here's where you can get tripped up if you don't do it wrong, and this is why we're going kind of from the bottom up, and this is why the grammar is in the order and form it's in. If all of these, if the add ops and the multiplication ops were just a single line in the grammar, then their order of operations would become ambiguous. Because they are separate lines in the grammar, because they're separate items in the grammar, it's enforcing a certain order to the parsing, which causes the order of operations to be preserved. So what does this mean? This means that whenever you traverse the tree, you will see the addition operation first, and then you have to go down to find the next child, and the child will be the multiplication operation, and then its component parts, and when that is traversed by the compiler, the multiplication operation will happen first. 3 terms, that's easy. Addition, 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 and multiplication. So what we expect to see here is this. And I need to find a way to make that bigger. Oh well. So if we look at the root node, it is an addition node, as I said. The first child is 3, and then the second child, instead of being 2 with a child of multiple I and 2 or something like that, is actually the multiplication node. So going through the grammar like this and working your way up creates this recursive tree structure, which is what the parser does. So at the end of all of this, you can pass it the sample program. This is gone. You can pass it the sample program where the tokenizer will consume the comment. Oh yeah, by the way, in Tiny, comments are in curly braces. The tokenizer will consume that, then it will emit 1, 2, 3, 4. It'll emit a bunch of tokens, and we will step through, and the parser will organize it. By basically, let's see if I can get both of these on the screen at the same time. And no one can read the thing on the right, can they? Okay. But basically, we pass a string of tokens into the parser and say parse a program. The program says, okay, I'm expecting a statement sequence, and the parser will look at the first token and go, okay, It is read. Read is a read statement. It'll go through and say, okay, I need a statement. So here's the first token, parse a statement, statement sequence. Statement sequence will say, okay, I need a statement, and then it'll pass that statement to the statement parser. It'll pass the statement to the statement parser. Yeah. Okay, so here we are. Which will look at which now we actually have a place which now when we're parsing a statement, we're at a place where we can where we have choice. So the first thing it does is it looks at the token type and says, okay, what type of token are you? And it's a read token. Read token is captured here. And so it knows that, okay, this is a read token, which means that I can consume this token. The next one I'm expecting an identifier, so go ahead and consume that token, make a read node, set the child of the read node, whatever this next token is. And the thing is that that's actually a really simple one. And the reason why we knew in the statement to check for read is because one of the things you're looking for when you're doing this type of parsing is you're looking for your terminating symbols, where you can go all the way through and be like, this is the first thing that I know to expect. And you can check for those, and then because you check for those, you know that it's right, and you can go back up and then consume the next one. So it's in this little thing here where we call the match method, which just consumes the token, and it ensures that the token you're expecting is the token that's actually on the list. Consumes the token, moves to the next one. Read name, which is supposed to be an identifier, so match checks and makes sure that the current token's like an identifier, consumes that, and then, okay. So now I need a read node, which is the statement, and it takes in the property of the token of the read token. And you do this over and over and over and over again. And it's boring and tedious, and you have to check everything along the way, which is why there are a bunch of tests for it. And it's also why I'm not going to keep going on about this, because it's boring and it's tedious, and if you do this for a job, you actually end up using the tools that I mentioned earlier that I'm not going to talk about, because it's a lot of stuff to talk about. And also, I think compiler's kind of cool. Oh yeah, by the way, I don't do this for my day job. This is entirely a hobby thing, so if you guys have a hobby you like, talk to Gunnar, and you can present it as well. Okay, so does anyone want to know more about parsing or have any questions about it or this particular step? No? Awesome. Okay, as I said, we're skipping error analysis and semantic analysis. Basically, those steps are you look for things that are wrong in your parse tree, and you either try to fix them or you report them to the user somehow. One of the things about semantic analysis is that you do also figure out the types of expressions. In the case of Tiny, since we only have Boolean and integer types, that's very, very boring. But that's where you would do things like, okay, if we had support for floats, in the semantic analysis stage, that would be where you say, okay, I have a multiplication option that's multiplying an integer and a float. Can I coerce this into something? Can I coerce, want that integer into a float number? Do the rules of the language or the rules of the compiler say that I truncate this float? And that's where that type of operation would happen if we were in a language that supported floats and if I was covering that. But Tiny's simple. It's supposed to be something that you can just kind of pick up and bang a compiler out in a few days and learn how it works.
Quick question. For the parsing, how is that, I guess, that meta language, the object structure, the domain model, basically, that you're creating, is that provided by the JVM or like some framework?
Oh, no. That's entirely bespoke. So a token is what's emitted by the scanner, and it's just something I made, and all a token does is it has a few properties. It has the type of token, if, then, else, next. It has an optional value, which is for integer tokens, a number. It has an optional name, which for identifier tokens is the variable name. And then it has the line number. The line number comes into effect when we're doing compilation, because in Java, the way that the Java debugger knows what lines of code match up to what items of bytecode is you insert an instruction saying, this byte, until I tell you otherwise, this bytecode is all at this line. So that's tokens, and then node is the output of the parser, and each node is basically an item in a tree. So a node has up to 3 children, and it has lots of optional properties. It has, well, not optional, but it has the expression kind for if this node is an expression, which is multiply, divide, add, a statement, if, then, if, repeat, read, or write, and then a node kind, which is basically, is this a statement or an expression? And this is all used by our switch statements to, when we're compiling and parsing, to know, okay, I have this type of node, I expect it to be this other, I expect this other thing. Is it this other thing? And it can hold a lot of metadata that the compiler can use to correctly compile.
I'm assuming you have used also some of those libraries that are out there to, I guess, create like, domain-specific languages.
Yeah, so there's one called Java CC that I'm going to talk about briefly because it's actually the one that NetBeans tutorials use for creating all of the tooling around their testing language, which is a simplified Java. So with NetBeans, they have 2 really good tutorials that also walk you through creating a scanner and creating a parser and integrating that into the IDE, which gives you all of those nice syntax formatting and syntax highlighting, and then the parser actually transmits its errors back into the IDE, so it can tell you things like, oh, this is supposed to be an integer instead of a float, this is supposed to, you have a semicolon missing here, you're doing this, you're doing that. The reason why I'm not going to talk about parsing errors and displaying those and integrating that is in part because error correction is as much an art as a science. You have to decide, you can't just look at the grammar and say, do this. Because what you'll end up doing is the first time something is missed, then you'll only ever see one error on the screen and everything else stops. So you have to understand enough about the language and enough about how the language is used to come up with a sane and rational way to handle those errors and continue parsing. Did that answer your question? Okay. Does anyone else want to see more parts of the code or dive into something more specific before I go on to compiling and translating? No? Okay, awesome. Actually, there is one thing in semantic analysis. It's kind of boring because we're using a stack-based machine, but if we were using a register-based machine, an actual Intel processor or MIPS or ARM, during semantic analysis, that would also be where we calculate the memory addresses for our variables. Since we're using a since we're using Java, we can just assign an integer to the variable the first time we encounter it, and just whichever number of variable this is that we've seen, that is the variable that is the address of the variable in the Java machine. And I'll show that instruction off in the compiling step, but that's just something to be aware of that I'm going to skip. So, okay. We have a scanner, we have a parser, we have a tree of nodes with all of our metadata attached. Now it's time to actually start recursing through this structure and creating bytecode. There are several tools to help with this step available in the JVM. One of them is Java P. I don't know what the P stands for, but it prints your bytecode out to the screen. And it works for okay, whatever. And it actually works for any class, any Java class file. And this is the so this is what the bytecode that the compiler that I'm talking about outputs. And as you develop a compiler, you'll want to start with those very simple programs. Just just push an integer to the stack, push an identifier to the stack, assign a variable, and look at the outputted bytecode to make sure it works. So, without getting into too much detail, a class file is arranged into several parts. There's the preamble, which tells you things like when it was modified, what the checksum of the file is, the source name, the class name, the versions of Java that it supports, and then flags about the class. You can see it's public, and I don't remember what super means. The next part is a constant pool. This is where Java records anything you might have imported. This is where it records these are the variables and type combinations that we want to use later. This is where it records these are the addresses of your various functions. And Java P is doing a lot of pretty printing where it's actually showing us, hey, this thing here is actually referring to the console method that returns java.io console. And that's kind of big. And then we actually get to the methods. We have our constructor, which doesn't do anything. And then we have our main method, which, if you remember from the code, it reads a variable, then it's...
Are those hash sign numbers, do those correspond to the numbers
Yes.
down below?
Up above. So yes, so Java bytecode, the bytecodes all consume an integer, and the integer refers to a location in this table up here. So invoke static number 17, if we go up to number 17 up here. I always do this. I point at my screen expecting you guys to be able to see it. And if we go to number 17 up here, we see that it's invoking the static method, and the static method is 13.16. But because it's nice to us, we know that this is the class java.lang.system, and the static method is console. And it also tells us the return type of console, which is java.io console. The L has a very specific meaning. In Java bytecode, your class signatures are weird, and they have extra symbols around them, so you can just quickly look at them and figure out what they are. But I can never remember, and the tools I use tell me what they mean. And then this is the actual bytecode for that method. Invoke static console, invoke the virtual method, which is another bytecode instruction, which means invoke a method on an instance of an object. And then there's another invoke static. So you see it's, first we're reading the, so console will, trying to figure out the best way to put this because it's actually really, really cool and you can't see any of it. As I mentioned before, Java is a stack-based machine. So invoke static will push to the stack the reference to the console. And then the next method, invoke virtual, expects the thing that you're invoking the method on to already be on the stack. And it may or may not push another variable to the stack. And if you ever emit bytecode where it's expecting something to be on the stack or it's expecting the wrong thing to be on the stack, then you get a very, very hilarious error that makes absolutely no sense, because Java throws up a stack trace for something that doesn't have a programming language stack. You get a java.lang.verify error or java.lang.bytecode error, or very low-level errors, which are really neat to debug. But it tells you the bytecode number at the very least, so you can look at this. But that's a method. The next part is local variables, which define the variables where the start, which is the first bytecode where they appear, the length, which is how long the variables are in scope from the start. Because Tiny doesn't have a scope, everything is just, once it's declared, it's in scope to the end of the program. Then we have our line number table. This tells Java this line of source code matches up to begins at this instruction. So that just keeps on going. And then we have the statmac table, which is used by the Java debugger to actually look at things when it's going back, I think. I'm not sure, but it didn't show up until I started including debugging information. So I'm going to assume that has some association.
Do you mind going back to that for a second?
Sure.
Can you scroll up?
Sure.
The offsets aren't sequential. Is it
Uh,
number of bytes? Or you're not intended to-
yeah, I think it's number of bytes. Now I'm thinking. So I think it's number of bytes. So invoke. Yeah.
Your actual code when you're doing the emitting of this, are you having to emit it by byte, or do you have tooling to help?
So this is actually where I do use a little bit of tooling. So in the compiler, I'm using a tool called JITescript, which is actually maintained by one of my coworkers. But it's it's a builder program, or builder patterned bytecode management wrapper around ObjectWeb's ASM library. So So what that actually looks like is, let's say we're compiling a simple expression. I have the root node of the expression. The first thing I do is I check to see whether or not I've marked this line in my bytecode, and I have not. So I create what's called an instruction label, and then I get the current block that I'm editing, and then I send a label, and then I send that label there. And then I emit and that sends a label, and then I tell it to, okay, attach to that label this line information for the expression node. So I get the line number from the node, and I pass it a reference to the label that's been scheduled to be put into the bytecode. And then I mark the line off saying, okay, I've marked this line in my bytecode. If you find this line again, it's already in the bytecode, don't omit it again. Omitting the same line over and over doesn't really seem to have much of a bad effect, other than it makes your class file bigger. But then getting to the actual nuts and bolts, we start seeing, okay, in the case of an expression, there's three types. There's an operator expression, which is we are doing some sort of mathematical operation. There's a constant expression, which is this is just a constant value or an identifier expression. The constant value is the easy one, which causes the instruction LDC, which stands for load constant, to be emitted. And all this does is it pushes an integer value to the stack. So, yeah, and this is where but you can see the man, code's so much easier when you don't have to tell people what it does. So anyway, but yeah, so this is actually emitting to the stack a single variable, or not emitting to this. This is pushing to the stack a single value. And then if we were, say, doing the identifier expression, then since identifiers are variables and we're interested in when variables are in scope, when they're out of scope, we do a similar check to what we did for the line number, where we find the line number of the expression. We get the name of the variable, and then we check our symbol table to see whether or not we are on a line, the first line where the variable appears. And if we are, then we want to emit a different instruction saying, a different label saying, hey, this is a variable, and we send that and we emit that label, and then we emit another label which provides the name of the variable and the type. And what will happen eventually is we'll do this for all of our different nodes, and we'll be emitting these instructions in order as we traverse that tree we created, and eventually we'll be done, and we'll call a method called, and we'll want to turn this into a main method, so you'll call block to main, which checks to make sure you haven't defined a main method already, and this is something I wrote, and then JITE script will define the main method, make it public, make it static, create the method signature, and then it will, and then that's actually now a method on the class. So when we call define, it will take all that stuff that's defined on the class, dump it out to a class file, and then return us a reference to that class object. So, what time? Okay, oh, it's only 8 o'clock. All right. I thought I was going to run. I thought it was much later than it is, but it's not. So I can go through like the compiler and the instruction selection if you guys want to see that, or I can move on to the tooling. The code is actually really, really simple, so if you want to review it after the fact, or we can talk about it later and go through it, but in the interest of getting to something that's a bit more visual, the syntax highlighting and the debugger and how all of that works and how that feeds back into all of the stuff that I've been talking about, I can go ahead and go to that, or we can do more compilers and talk about instruction selection and traversing the tree. No, wait, yes? I see a no and I see a yes. Instruction selection? Okay.
But that's just me.
You're the only one who said anything. Everyone else is just kind of like, okay, get on with it. Yes? Yeah?
For the function in the compiler context that you're showing us, is that basically converting the tree into the stack?
Yes. So, well, no. Which function?
The one that basically you saw that it was a switch statement.
Yes, that's where the tree starts turning into the stack. Okay, so all right, so we'll run through the compiling, and that's part of instruction selection. And again, Tiny is a very simple language, so this really doesn't take much time. To put it in perspective, it took me it took me about half as much time to write the compiler as it did to write the parser, because the hardest part is getting the order of the tree correct. So in our compiler, the first thing we do is we call compile program, and we pass it in a parsed tree. We also pass it in an initial context and then the symbol table. The symbol table is just a map. It's basically whenever you come across a variable during parsing, you say, okay, add this to the symbol table, and here's the line number, and yeah, it's just a map. There's nothing special there. So as we know from our grammar, the first thing in a program is the statement, is some statement. So our compiler will look for our compilers first will compile a statement which creates a new, which gets the current code block. In the case of Tiny, since we only have one method, since Tiny doesn't support methods, we only ever have one code block, so we don't get to define a bunch of methods. So you're going to see current block a lot, which is just the current block that's being executed. If it did define methods, then at a certain point we would have to define the method and then create a new code block, but that's not part of the language. So we have a statement, and we know that there are only a few kinds of statement that it could be. An if statement, a repeat statement, an assignment statement, a read statement, or a write statement. And you can see that from the right here. I mean, and that's just straight from the grammar. It's the only thing that can actually be possible. And so what you'll want to do is handle each of these differently. In the case of if, what we have is, in the case of if, what we have to do is we have to define several labels in code for where to jump to depending on the Boolean value of our test expression. What we know about from when we were parsing is that with the if statement, with our if statement, the first child will be the expression. The first child in the node will be the expression. The second child of the node will be the statement sequence. And then the third child of the node is optional, which is the else statement. This is all assembled during parsing. And that's just a rule of the parser. There's no reason it has to be that way, but it's just what makes the most sense. What's important is that your compilers and your parsers and your scanners all agree on certain things like the order of children and what they mean in relation to your grammar. So I define two labels, the else label and the after else label. Unfortunately, I don't have a whiteboard or anything, but the way this code works is, well, first and then we have to compile the expression of the, oh, this was a terrible one to start with. So okay, the first thing we want to do is we want to compile the expression that handles the test expression. There we go. And what this will do is, I should have started with an expression, not a statement. Anyway, but you know, if it's something like x minus 3, if x is less than 3, then that's an operator expression. So the operator expression has, as part of it, two simple expressions. So I want to compile the first one, and then I want to compile the second one. X less than 5, so that means that the first node in that expression is an identifier. So what I want to do is I want to get the current block, and I want to omit the iLoad, which stands for integer load, which loads a variable and pushes it onto the stack. And that is, and I look up the address of the variable from the symbol table. Okay, so back to it. If x is less than 3, the way that parses is you have an operator expression with two children, an identifier expression, and an integer expression. And the way that compiles is the first thing it has to do is it has to load that, it has to evaluate and load that identifier. And the way it does that is by omitting the integer load instruction and passing to the integer load instruction the address of the variable that the symbol table has calculated. As I mentioned earlier, since this is a very simple machine and not a register-based machine, the addresses are just linear, can be just numerically linear as you encounter the variables. So x is the first thing we encounter. It will have an address of 0. The less than is still the parent node, and we have to evaluate the other child. The other child, 5, is a constant, and that one's really easy. Load constant. And then finally, we've evaluated our children, we've pushed our children to the stack, and what's next is to actually have the operation and push that to the stack. And this is where this add operator method comes in. X less than 3, we have we get from the node what type of operation it is. We know it's less than. So this means that we have to have, because this is a Boolean expression, we have to evaluate it and then push one of 2 values to the stack. Since we don't know what X is at compile time, what we have to do is we have to use a jump. And what we do is we create 2 labels. If it's not equal, then this is really where I wish I had a whiteboard. But basically imagine, if you will, a stack of instructions. The first one is the jump instruction, and that's what this is. If integer compare greater or equal, okay. It's very simple to think about, but it's very difficult to explain because we're turning a tree structure into a linear thing. But basically what you want to do is you want to have the instruction, the test, what to do if the test is false, and then a jump to jump after the test. And then if the test is true, then you jump to...
Is that block and then the series of statements following it, or the series of functions that are invoked, or methods that are invoked on it, does that output a block of JVM code?
Yes.
Virtual machine code?
Yes. And actually,
So why don't you just take that block of code and then point to the code it emits, and I think everybody will get it.
Thank you. That's a great idea. Okay. And this is the block of code that it emits. The first thing is if compare, which looks at if compare greater than or equal, expects 2 values to be on the stack that are both integers. That's what the I stands for. If it is true, then push 1 to the stack, which is true, and then go to line 21, which also pushes 1 to the and then go to line 21, which also pushes 1 to the stack because this is a series of compares. But basically, go to the next instruction. If it's not true, then push 0 to the stack and then just continue on normally. And what the code here does is we label, okay, if it's not equal, then here's the jump for after the true, and then there's the label that is at the end of the expression. So it's evaluate, push true, jump, or evaluate and jump, push false, and then continue.
Okay, the I constant things make sense. The label things don't make sense yet.
Yeah, and that's because the labels aren't the labels are basically what these guys are. The labels are just identifying the jump targets. Because of the fact we're turning a tree into a linear structure, we have to be kind of creative with our jumps. And this is actually one of the things that was really, really hard in... Yeah. This was one of the things that was really, really hard in undergrad to wrap my head around. And this is actually something that took a whole day lecture to do.
Is it populating the after variable or after equal variable with something?
Yes.
So
Well, I mean...
non-label thing fills that in with some pointer so you can use it later.
Right, yes. So what JITE script will do is it will see the label, translate that to an address, and then turn that address into a property for the bytecode instruction, which is the jump target if the value on the stack is false.
So is this like almost you're mapping each statement over like assembly or bytecode? You have to kind of instruct it how it needs to go.
yes.
Almost like mapping. I mean, if you have to program in a separate language, it's almost like this.
Yes. Bytecode is basic. I mean, yeah, bytecode is a very low-level machine code for the JVM. It is the JVM's machine code. So, if we were actually writing a machine, this would be the labels would reference instructions in memory, and this guy would be a jump instruction instead of a comparison, and it would take something out of memory, compare it, as opposed to looking at what's currently on the stack.
So do you have a dictionary of what the codes are, byte codes are? Do you have those? And do you know what the codes are?
Yes, I do. Wikipedia does. So I probably should have brought this up earlier, but all those bytecodes actually mean things. And AA load loads a reference from an array. A is either an array or a reference. I don't know why A got overloaded to be those. But as you can see, it's, a constant null, push a null reference onto the stack. So what each instruction does is it consumes variables above it on the stack and then pushes something before it continues. And that's really what you have to think about when you're putting this thing together. So in the case of the if statement, what you want to do is each child of that expression will, when it is finally resolved and processed by the JVM, will be a single value on the stack. And then the other child will be another value. And then the if compares the two, and if integer, and so the instruction we were looking at, if value 1 is greater than or equal to value 2, the greater than, branch to the instruction at branch offset. So what that means is, so what we're wanting to do as part of this if statement is, since we're evaluating a comparison operation, we want to condense that down to either a 1 or a 0. And the way we do that is, because it's a comparison operation, we put the two values down, we execute the compare, and then we either push true and then jump to after pushing false, or we jump to pushing false.
So is there multiple ways to map the statement to bytecode?
Yes. Yeah. That's also one of the things that's very, fortunately, Tiny is a simple language. So if you understand the few basic constraints, especially around jumping and binary evaluation, that's kind of the hardest thing there is to wrap your head around, is that you have to have those two jumps in there. But what you're always wanting to do is condense things down into single values on the stack for the next thing to consume. It actually doesn't matter if you have extra values left on the stack when you return, as long as they are the right type. If you have incorrect values on the stack, then you get a JVM exception. If you run out of values on the stack, you get a JVM exception. So for things like a return statement without a value, you'll actually push null to the stack before you do the void return.
Can you go up where you instantiated block, or you did the new one, block?
The new block? Sure. All right. So new compiler context and compile program. Yeah, so when I instantiate the compiler context, I get a default block to work with. Sometimes this will be, and this is just whatever block of code you're currently processing. And it really doesn't matter, because you don't assign it anything until you're ready to turn it into a method, which is done here at block to main. So when you call new compiler context, there's just an empty block of code that you just immediately start adding to. And then when you finish adding to it, you define it as a method. And new code block is something that is provided as a static method from JavaScript. And it does, so this is me calling the JavaScript, which calls ASM. Does that help? Or, but basically when you get a code block, it's empty. So the first thing you'll do is you will push some, so in the case of our program, the first thing we do is we push a static invoke. So read is special. So you remember how the first line of our program is read x? What this means in Tiny is it means read an integer from the console. What it means in English in Tiny is read an integer from the user and store it to the variable x. When we parse it, it's the first variable we come across. So x is assigned a space in memory of 1, or an address of 0. So if we look at read, no, I'm in wrong. So if we look at read, the way we read an object from the user is we have to invoke the console method from Java off of system to get a reference to the console, and then we ask the console to read a line of input from the user, and then we invoke the parse integer method. And the console, when it reads that line, it pushes it to the stack, and then we invoke another static method on the integer class parse int, which takes the string that's on the stack, consumes it, and then pushes an integer onto the stack, or throws an exception. And then we store to memory, that's what iStore means, integer store. We store to memory the value that's on the stack, which was emitted by the parse int method, and we store it to a location in memory equal to the address of the variable with the name of x. And that, in bytecode, turns into these first 4 methods, or first 4 codes. The tests, so the tests that are associated with this break it down in a lot more sane order. So if you get a chance to look at the code afterwards, it's actually not that terrible. All right, does that help? Okay. So we've got about 30 minutes left. Are there more questions about compiling? Is there more cases you want to see how it resolves, or me to try cool things? Okay. Yeah. Syntax stuff? All right, syntax highlighting. So I'm going to not get into as much detail about the how NetBeans operates, because that's just the really boring stuff of this is, it's just calling a bunch of NetBeans APIs, but then the actual theory of how this happens is, well, kind of doing things is actually kind of cool. So what we want to do whenever we're implementing tooling is we want to think about kind of the common things that we're doing. And we want to think about, in the case of syntax highlighting, we want to find a way to represent what tokens come out of the scanner. Syntax highlighting and tokenization are very tightly coupled to each other in terms of, in the sense that the syntax highlighter consumes directly from the tokenizer. When we're doing error checking, that starts happening with the parsing and other parts of it, and that's stuff that I haven't implemented. But if you want to learn more about that, look on the NetBeans website. There's a Java CC scanner and Java CC parser tutorials, which are actually really, really good. So I'm going to be switching back and forth between 2 IDEs, and I apologize for that. In NetBeans, The way that NetBeans works is you create modules, and you define a module in a layer file and a manifest. And the layer file, why is it doing that? All right. The layer file defines fonts and a style file, fonts and colors. And here's stuff you might recognize. It says, okay, for tokens named blah, default them to this style, and the style that it's defaulting to is provided by the IDE. So the character style, the identifier style. Well, how do we associate those names with our tokens? For that, we look at the lexer. And there is some boilerplate associated with NetBeans that gets all of this loaded up and into the IDE, and we're going to skip all of that, but what NetBeans does is it instantiates this lexer object and starts passing in, well, what NetBeans does is it takes what's in the editor, instantiate a lexer object, and passes that to the editor. And it provides a lexer information object, which has a reference to the input. And so since we already have our tokenizer, what we need to do is we need to extract all the tokens and then step through the lexer and tell NetBeans as we consume them. Because the tokenizer is a separate thing, we end up doing something that we set it up the first time through, and we get our list of, we consume everything off the input, restart the input, and then we consume blah. So, all right. The first thing we do is we get from our information object from NetBeans the input object. And then we do this, which everyone who's ever written Java has done 1,000 times, where we consume everything off the buffer, put it into a string object, into a character buffer, and then we pass that to our scanner, which is our tokenizer or lexer. We instantiate it. Well, we don't need a new parser. Then we create a string buffer by wrapping the. Why are we doing? Yeah. Oh, and then we create a string buffer. We reset the input back to the beginning of the tokens. So now our scanner is ready to start scanning, and NetBeans is told, okay, we're at the beginning. And then we have our, and then we just say we don't need to initialize again. And so we go, so then we get the first token. We check to make sure we're not at the end of the file. Check to make sure we're not at the end of the file. Then we get the position of the buffer, which is the character buffer that the scanner is wrapped. We get the next token from the scanner. We do error handling. And then we get wherever the scanner has advanced our buffer to, and we tell NetBeans we consumed that many characters. And so, and then we go here, where we return to NetBeans one of its token objects that takes the token type, and then we go to here where we return to NetBeans a token object which takes the token type of the token returned from the lexer. And this will be one of comment if then else end, which is how NetBeans, actually there is one more step. Here it is. NetBeans will look up the token type that we pass it against this data structure that we created here. So if it has an if token, then that gives where the keyword assignment happens. I forgot there was so much error checking in that. The reason why there has to be that much error checking is so that when I start typing in NetBeans, I don't have errors, because this should be a error, because I have a nested comment. Tiny doesn't support nested comments. That should be an error, but I had to do a little bit of error checking in that tokenization phase. So that's why it's kind of nasty. I did it late at night. Does that help?
Just for context, the tokenizer you're using is the same. It's just the tokenizer is standard. That's the same you had in the compiler.
Right.
And then the tiny, what you're calling the tiny lexer, is actually essentially the glue between that and that.
Yes, it's the bridge between my compiler and my tokenizer and NetBeans' tokenizer. Yeah, NetBeans passes a object which represents the structure, and we're supposed to return a token that is the token for the state that the lexer has been, that NetBeans' lexer has been moved to. And all of that was just to accomplish, and all of that other stuff was just to accomplish that. And the error checking was to make sure that I could type and I wouldn't end up with, you know, just crashes and errors.
So right there, is it passing an entire file?
Yes.
The lexer, it's not just the current line?
Yes.
So is it typing, it's reinterpreting the whole file?
Yes. Yeah. Have you ever wondered why your IDE suddenly grinds to a halt whenever you have a big file open and you start banging out as quickly as you can? Fortunately, tokenization is actually really, really, really quick, and it's one of those things that computers are really, really, really good at. So if you think about it, it only takes a few cycles to read the value and then compare it to a table, and then you compare it to the next one, and then you assign it a value. It's operating at billions of cycles a second. So assuming you don't have a 100,000 line, 10 million character file, you're probably fine. You only have 3 of those? Okay. So basically you write a lexer object that translates from your scanner into NetBeans' stuff. And then the really cool thing is the debugging. And this is really why I like the JVM, because the debugging kinda, sorta, I got for free. I had to write some really boring like action handlers in NetBeans that basically say, okay, this file can, so going on a little bit of a tangent about NetBeans, each element on the screen, the editor, this gutter here, this node over here, they all have different names and properties and actions that they can respond to. So for instance, toggling a breakpoint action, we can annotate the toggler, say, okay, on tiny files, I know how to handle the toggle and the breakpoint event. And all this does is it gets to NetBeans' debugging framework and say, okay, put a breakpoint here, put a breakpoint here, put a breakpoint here. And then when we say debug the program, all we're doing is we're calling my compiler, which creates a class file in the temp directory. We're setting our class path, basically, and we pass that to JBDA. And then we just tell, okay, open up a terminal, run the program, and start Java in debug mode. And because we inserted all of the debugging information in the bytecode, we can just tell Java to load this class in debug mode and tell NetBeans, hey, and tell NetBeans, hey, you can set breakpoints on this class file, and then Java does the rest for you. And that's really where, like, all this long, rambling, boring, okay, this is a parse tree and blah, blah, blah. Like, this is why all of that was important is so you can get that bytecode on the JVM, and then the entire Java ecosystem is now working for you. You can package the class the tiny class up, import it into a Java program, and then call that main method. Now, tiny's main method doesn't have any return type, so all you can really do is just invoke that code from Java, and it only deals with integers, but it's not that hard to take that extra step of, okay, now we're going to have, now we're going to say support a, let's say we want to do something like 3D math, and we want to create a vector type. You can now create, using these techniques, a simple language that understands cross products natively. So you can have using Unicode, a matrix, and pass that into your compiler and get Java bytecode out that will execute on the JVM matrix multiplication. This was actually one of the first JVM languages. It was called Fortress, which basically ran on the JVM typographically accurate and correct math. And I saw that in late 90s, and that's kind of what made me think this was really, really cool. So while Tiny is simple and while Tiny is very, very restrictive, the fact that all of that can get on the JVM and the fact that it's very simple techniques that you can apply over and over again make integrating with all of the Java tooling very, very simple. I mean, you saw all I have to do is, okay, NetBeans, this is what these tokens are, and I have syntax highlighting. Okay, NetBeans, you can set debugger breakpoints, and because I compiled the debugging information in, that worked. If I wanted to, I could have, there's, like I said, there's something similar to the Lexer for parsing. Hey, and NetBeans will start saying, oh, hey, you've got these errors here. If I had the error handling and typograph and the analysis tools written, then I can even do code completion and code hints, and that's all available, for very, very easy, and it's all because of all of those very, very simple things you did at the beginning. All right, so now it's time for questions. Yes?
So how easy is this to replicate in Eclipse? Netflix is very Eclipse.
I can't imagine it's too difficult, but I haven't looked. I basically flipped a coin between IntelliJ and NetBeans and landed on NetBeans. I can't imagine it will be much more difficult to Eclipse for Eclipse, because if it were, you would not see so many awful Eclipse plugins. Anyone else? Okay, so anyway, here it is again. Let me make sure I got everything. Yeah, I got everything. Here it is again. The links to the source code, if Mozilla will cooperate. Yeah, the links to the source code. I'm second son on GitHub. It's Tiny and Tiny NetBeans module. I have lots of tests, so you can, if you want, just take the test files out and run through implementing those and use the TDD patterns. Yes, Phil?
You have you mentioned books. You have like a bibliography of what you...
So most of what I looked at was a book called, come on, Android, don't suck. It's a tall order. Yeah, I actually did explicitly write it down. I just didn't include it in my... the name of the book is Compiler Construction Principles and Practice. I'm using the second edition, which was actually published in 1995. So imagine a compiler's book that talks about, stack-based machines and how, nothing uses them because Java wasn't a thing yet.
Pedro and Olin, is that the one?
There's
Pedro and Olin.
3 I remember from school. Dragon book,
Mm-hmm.
the big red book,
Mm-hmm.
and then I hate to say it, it's a tan color book.
Yeah, no, I can't remember what the Dragon book is, but okay. And then there was another really good one that was published in 2013. And these books are like the reason why I'm using the 1995 edition, because it's a shorter book at only 500 pages. Most of those are actually typed out code. Like the book actually has an implemented virtual machine for the tiny language for you to target instead of targeting your processor. But the current edition of the book is over 800 pages and includes things like how to optimize your code generation for multi-core architectures. Yeah, how to detect all of these weird like race conditions in your code, and has all of the optimization stuff I skipped and has a lot of error correction stuff I skipped. So yeah, but that was the book I used the most, Compiler Construction Principles and Practice. Okay, anything else? Yes?
Can you extend an existing language with new types and new operators using this technique?
Yes. So the way you would extend, so the question was, can we extend an existing language? And the answer is yes. You would have to either A, extend the tooling available for the language, and the difficulty of that is based on the difficulty around that particular tooling. Or B, hope that whoever wrote the tooling wrote it in a way that was easy to extend. In the case of Tiny, if we wanted to include floats, we would create a new token type, extend the tokenizer, and then in the parser, in the parse tree, well actually not in the parse tree, but in the semantic analysis, we would have to understand what to do when we had different types in an assignment, when we had, say, an integer and a float interacting with each other. How do we resolve that? And what you might end up doing is, in your type analysis, say, okay, this integer node now is a operator node that casts to a float, and you would transform your tree. And then once you've done that, you don't have to edit your compiler, because your compiler knows how to omit. And then, well, actually, no, you'd have to edit your compiler enough to know how to deal with that transformation operation. So you'd have to add to it, but because you understand, because you've already, but it's not going to be that difficult. Like, I had to add in support for comments, because before, my Lexer was just throwing those tokens out because the compiler didn't care about them. But when I went to implement the syntax highlighter does care about them. So I had to create a new token type of comment, and then teach the tokenizer how to consume it, and then teach the parser how to ignore it.
But you have to have access to all that code in order to modify it. That's something like.
Right, yeah.
What if you did, is there a way to, like, for example, like just Java,
If you wanted to extend Java. Yeah. I'm trying to think.
You can also, I mean, one thing I've done a lot, I haven't done it through committing code, which actually that's kind of intriguing at this point, because Java's allowing a lot more dynamic code generation where you can actually create a class on the fly and execute it.
Mm-hmm.
But you can, it's like if you had a language of your own that you want to kind of expose to your users, it does something like expression evaluation. Well, I could implement that, and then that just becomes something in the code. You're in full control over what that syntax looks like, what those restrictions are that the user has. So you can create the playground you want them to play in and leverage that. And I've done it just interpreted essentially.
Yeah. A better answer to your question is, if you're maintaining your own library or your own language, you will probably be using something like Antler or something like Java CC or something like Lex and Yak to generate your scanner, your toker, your parser, and to a lesser extent your compiler automatically. So you would edit your grammar, and then you would have your tools recreate everything, and then you just set up the last little steps. So that's actually how you would do it if we were working in the real world and not the theoretical, I wanted to write a compiler, and I did world. Anything else?
Can you embed JVM code right in Java like you can assembler in C?
Yes. Ish. So what you have to do is you have to, you'd use, oh, I'll just show you. So as part of this, I borrowed from the din.js project this thing called the dynamic class loader, which is a class that you pass into an instance of the JIKE class that you've created all of this bytecode in. And what it does is it gets the bytes from JIKE class. So this is just a byte array that anything can create, which represents your class file. I write it out to the temp directory, but you don't have to. But we've got the bytes.
Summers, is this out on your Git?
Yes, it is. Oh, there it is.
So you write out a file with a dot class that happens to have all the bytes in the correct order for a class, and then load it with normal.
You can do that. Actually, you can skip. Yeah, that's what I do in the debugger. But actually, you can skip all of that and call define class with the JIKE class thing. And oh no, you still need the bytes. So, yeah. But yeah. So, this is just.
It's just the binary, so that's,
Yeah.
it's the same thing a lot of the things like Groovy does.
Oh yeah. Okay. This is java.lang.classloader. You pass it the class name and the class bytes, and it returns you a class instance. Not a class, an instance of the class type, not an instance of your class. So yeah.
And then what helps me get those class bytes correct?
I use JITescript, and JITescript internally uses Object Web ASM. So those are tools you can use, those are libraries you can use. And the way that works is you just say block and then instruction, 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 instruction. There are other tools you can use, like the compiler tools that generate a lot of this stuff for you. Yes.
Is that just simple? I try to add A plus B.
Yes. So because Tiny doesn't have a return type from its program, it's kind of hard to, I had to actually inspect the generated bytecode. I started out a little over a year ago writing a Lisp compiler, which evaluates to a single value that then gets returned. So,
You're just a glutton for punishment, aren't you?
so what that looks like is what this looks like is this, where so I've created a run. So this is actually a completely different project now. I created a run method which takes in a program that evaluates to a value, and then whatever value it evaluates to gets returned to Java as an object, and I'm casting it to a Boolean and inserting true. And the run method compiles the program, and the compile method returns a class instance. Internally, it's using JIKE class, so JIKE class gives me the bytes, the Java class loader gives me the class, and then I instance it using reflection, new instance, and then I get a reference to that main method, execute it, which returns just the last thing on the stack, which is whatever the Lisp expression evaluates to, and then I just return method.invoke. So yes, you can, and that's an example of it.
Did you mess around much with bytecode manipulation packages when you were working on this?
I mean, just not really. Like, I didn't work with CG or anything like that.
What would you do if Tiny had a pointer type?
Internally, that would be referenced as a internally that would be represented as a reference type, which is all of these like which is a store. So whenever you got the pointer, you would just store the reference versus storing the object. Even in the bytecode, you don't get true pointers. So if you wanted to try true pointers, what we would end up having to do was allocate a buffer of memory and then maintain that block of directly allocated memory using Java behind the scenes. So you would omit the different operations whenever you had your pointer operations. Is what you'd have to do, because the JVM doesn't give you access to pointers. So you'd have to create something that worked like pointers. At that point, I might actually start looking at writing an interpreted language instead of a compiled language, or writing a compiled language that targeted actual hardware instead of the JVM. Or you could, if you really, really, really wanted to, use Jindy to handle the pointer manipulation, and then your Java would be calling native C code. So even at the bytecode level, Java really doesn't support pointers, is where all of that is. So you have to figure out what you want pointers for and then emulate that. It's kind of like before we had invoke dynamic, where with Groovy, they had to generate all kinds of stuff. Well, they'd perform lots of analysis on your code to figure out all the possible methods that might be called on your object, and still, when it compiled the object, have like just generic method handlers provided through the reflection API that got called, which was why it would get really, really slow sometimes, and what invoke dynamic was made for. So you'd just have to emulate it using Java.
I mean, I guess part of it is you want pointers that are hardware addresses, or you want pointers just as some concept like pointers in there?
So thinking about if you wanted to run languages that have pointers on the JVM.
The actual language, like a C program, or
Any language.
your language implemented on the JVM.
Yeah.
It's gonna, your physical memory is just going to be some data structure in the Java program.
You would also have to have ways to marshal and unmarshal your, like, let's say you have, let's say we have something like a structure in C, and got 3 minutes left, so I'll be brief. Let's say you're in a language that supports structures, and a structure is just, okay, this is the order in memory of some values, and you have a pointer to that structure which points to the first section of memory, or points to an address that what you would have to do in Java is you would probably write a Java class file that was responsible for taking an array of bytes and turning it into an arbitrary structure type object, and making all of that work behind the scenes. So you'd still have to emulate, and you'd also have to do lots and lots of casting. And the answer is I've tried this, and it's very slow in Java, because you have to emulate a bunch of things that you get just for free on hardware. Like on a processor, you can just say, these bytes, at the end of the day, you're just like, okay, and render it as a string. And if you remember back in the original C days, whenever you say render this as a string, you could do that.
Is the JVM being extended at all to
help with that? Is anybody recognizing it, or anybody really want that feature and likely to put it in the JVM?
If so, it's kind of a design decision that the JVM can't do this. that it is, very statically typed, that it is very secure. If you want to do this, this is where Jindy and these other tools come. Is it Jindy? No, JNI, not Jindy, JNI. Jesus, I've been in the EE land for too long. JNI, Java Native Invocation, where it calls C code that does this for you. And you can pass into Java, you can pass into the C code, hey, give me whatever's at this memory address, and then the C code will return you a byte array that you can do with as you will, which is actually from memory. There's also the concept of a directly allocated byte buffer. And then there are also the unsafe operations in the Sun packages that you can also use to get direct access to the memory. Were you just saying I'm out of time, or did you have a question, Gunnar?
No, I was just thinking.
Oh, okay. And I know that was a really crazy roundabout answer, but the answer is, if you want to do something like that, you have to emulate them, or you have to use native code. Which I suppose if you're running C code in Java to run C code, you're, yeah. Anyone else? Going once? Going twice? All right, thank y'all.